And it's a tribute to the great mathematician Maryam Mirzakhani. Well, yeah. And today I'm talking on Fourier series, classical and modern aspects. So it's going to be a very, there'll be no technical part. So it's like a story, the development of Fourier series until now. So yeah, so let's see what are Fourier series. So Joseph Fourier defined Fourier series while studying the evolution of heat equation with boundary conditions. So let us first define the heat equation. So let Tx comma T represent the temperature of a thin rod of length 1 at time t. Okay, it should be pi, I'm sorry for the typo, x in 0 comma pi. And this is the heat equation, which the temperature follows for x between 0 and pi and T positive. And then the boundary condition is that the temperature at 0 and pi for all time is 0. So this 0 is immaterial. You can choose some other constant also. And then another condition is that at t equal to 0, that is time equal to 0, the temperature is already given to you. Of course, you can measure the temperature, right, of the rod. Then one can check by using separable of variables method that if you put Tx comma T as this, e of minus n square pi square T sine of nx, it satisfies the above boundary problem with the initial temperature as sine of n pi x. So n is an integer, and this is the initial. If I start with this initial temperature, then the heat evolution of the temperature will be this, okay, on the rod. And another easy thing to verify is that if you just take this sum, you multiply this with a constant, you call it Cn, and if you take a finite sum, this will also satisfy the above problem, because for each function the boundary values are satisfied, and then it will also satisfy the PDE which is given to you. So that's just a simple thing to check. So then, when Fourier was studying heat equation, so he wrote a book called The Analytic Theory of Heat, and there he claims that one can write a reasonable function. So this reasonable is in quotes because that took, centuries for mathematicians to figure out that what is that reasonable function, which is defined on, again, initially I started with 0, 1, and then I sort of scaled it. So at some places I'm forgetting. So it's 0 to pi, such that if it is 0 at 0 and pi, basically his claim was that any reasonable function on 0 to pi with such that its value at 0 and pi is 0, it can be written as a sum of these sine series. So, this may not, how should I say that? Yeah. So more generally, if you have a function, so because this is an odd function, so you can, talk about it and minus pi to pi, this is an odd function, which is 2 pi periodic function, okay? Then, so one can ask that if any odd 2 pi periodic function is just a sum of these sine nx, an times sine nx, then for the even functions, similarly you can develop the cosine series, and the same question is for the cosine series. Then to sum up the above two questions, it becomes that if any reasonable 2 pi periodic function can be written as a series of sines and cosines with these discrete frequencies. So this n is also called a frequency. So in words, the question is that if any 2 pi periodic function is a superposition of functions of the type sine nx and cosine nx, 2 pi periodic on minus pi to pi. And then if it is periodic, you can extend it on the whole real line. So you see, just posing this question is easy, but to make sense out of it mathematically is not simple, right? Because from a mathematician's point of view, there are many things to be taken care of. First question is that if for a given 2 pi periodic function, it satisfies this equation, which I have written here. So is the series, how does the series converge, right? Is it converging pointwise or is it converging uniformly? And then how are these ANs and BNs related to F? these are, so they should be determined from f also. No? Somehow they should be related with the function which you are considering. So you see, the second question is still can be figured out, and then the first question will take some time. So let us look at first the second question. So, okay. Then by using, so let's first simplify this equation 0.1. Then by using Euler's formula, we can rewrite. Suppose this series exists, we can rewrite in terms of these exponentials, e of I and x, n over integers. So once we determine these Cn's, we can determine An's and Bn's and vice versa too. So we just stick with this sort of expression. And then, these exponentials, they satisfy a very nice orthogonality relation that if you take e of I n minus, so this I think everyone must have done in their higher secondary class. So, let us assume that f of x is summation Cn e of I n x, and assume we can integrate f on minus pi to pi. And then we are going to use this formula now, you see. So basically this formula says that if n is not equal to m, this integral is 0. And if n equal to m, that is, this will be 1, this will be 2 pi. Okay. So now let us compute this. You integrate f of x against e of minus mx dx. And then you write, because we are assuming that fx is the sum of these exponentials. So you write it this way. And then, if we can interchange the integral and the sum, then by using that formula for this integral, you will just get Cm. So basically these Cm's, so provided all these interchange of limits is satisfied, you can recover Cm's from the f, basically given f. Okay. Then if we define En of x is e of I n x, and then we define the inner product like this, integral minus pi to pi 1 by 2 pi fx gx bar dx. You can write this formula, the previous one, this formula as in the terms of the inner product. So basically, those who know functional analysis or linear algebra, this is inner product, and they are, so this tells me that they are orthogonal. En's n ranging over the integers. Okay. So for f an integrable function, we define f hat of n as f inner product En. So this is called the Fourier coefficient of f. Then we call this, because you see this Cm is nothing but the Fourier coefficient of f at m. So we can just write the sum in terms of the Fourier series. So this is called the Fourier series of f. Okay. And then we define the partial sums, because you see, to make sense of the convergence, we have to bring in certain notions for it to be more precise. So you define these partial sums. So basically, you take the sum of f hat n En for mod n less than or equal to capital N, where capital N is a fixed positive integer. So now we say that if this partial sums as n tends to infinity, if it converges to f, we say that Fourier series of f converges to f at x, because you see this is a function at x. Okay. And now the question becomes, given a reasonable 2 pi periodic function, does Sn of f converge to f pointwise or uniformly? Okay. So this sort of simplifies our question a little bit, but the answer is not. So before going further, let me recall what is pointwise convergence. So we say that Sn of f converges to f pointwise at x if this limit n tending to infinity Snf at x is equal to fx, just at x. Okay, this, so basically all your epsilons and deltas may depend on x. So we say that Sn of f converges to f uniformly if you first take the supremum of the difference of Sn of f at x minus f of x, and then take the limit n tending to infinity, that is equal to 0. So you see, this is a very strong convergence, right? And okay, I think this is all. I don't know. All right, so one of the earliest results, which this question of convergence of Fourier series, it has intrigued mathematicians from centuries, and then the first sort of result was obtained by Dirichlet in 1829. Okay, and in those times, even the notion of functions was very limited. Okay, so this is the theorem that if f is a piecewise C1 function, that is the derivative of f exists at all points and the derivative is continuous except on finitely many points. If it is a piecewise C1 2 pi periodic function, then Sn of f converges to f uniformly. So this was one of the earliest results. So you see here, this theorem, it demands some sort of regularity of f, right? Because we need it to be differentiable, and also the derivative has to be continuous except on finitely many points on the interval minus pi to pi. But you see, in many of you might have seen this in your first course in analysis, that in fact, but there are continuous periodic functions which are nowhere differentiable, right? So there is a whole class of those functions. So this certainly gives you answer, but sort of partial. And in fact, in 1873, Riemann constructed an example of a continuous periodic function whose Fourier series does not converge at one point at least. Because here, whenever you are considering continuous functions, you would like to have the convergence uniformly. So if it does not converge at a point, then you cannot expect uniform convergence. So we need some regularity assumption on the function for its Fourier series to converge to it, right? And well, there is a result which I'm not stating, which is called alpha Holder continuous, and alpha has to be bigger than half. Well, so now this was all about pointwise convergence or uniform convergence. And now let us go to some other modes of convergence, right? Because if so, like there are some examples where the pointwise convergence fails. So then mathematicians would definitely like to go to some other limiting theorem, right? So one such mode of convergence is, instead of pointwise convergence, one could ask if SNF converges to F in the L2 average sense. That is, you take the difference, you take the mod square, you integrate over the interval minus pi to pi, thus go to 0. So this is some sort of L2 average, right? And so, but this, for the above kind of convergence to make sense, the whole theory of integration needed a complete makeover, basically, because people had no idea how to really solve it. And it actually took almost 100 years from the time the question was posed by Fourier for the above question to be answered. So in 1907, after all these measure theory was sort of making sense, Ries and Fisher independently proved that if you have a square integrable function, that is, this integral from minus pi to pi f of x mod square dx is finite, and of course it is Lebesgue integrable, then this L2 average goes to 0. Okay. So at least we have something in the averaging sense, but then there is a lot still to be discovered. So just taking slight digression here. So just to interpret these partial sums, those who know functional analysis, they can see that. So I'm just writing it here. So you see these exponential e of, so, I mean, this will give you some sort of motivation that why Fourier series are also very natural. For example, just look at this e of I and x. So it's a 2 pi periodic function. And if you apply this operator, if you take the two derivatives, multiply by minus, you'll get n squared times e of I and x. So basically, this exponential is an eigenfunction of this operator with eigenvalue n squared, right? And f going to f inner product en times en plus f inner product e of minus n times e of minus n can be viewed as projection onto the eigenspace of this operator with eigenvalue. Well, it shouldn't be minus n squared. I'm sorry for the typo. It's just n squared. And then this limit, this limit Sn of f equal to f in L2 is nothing but the spectral resolution of identity in the Hilbert space, this corresponding to this operator. Okay. And those who have not done Hilbert spaces, you can also think about spectral theorem for self-adjoint matrices. So because this operator can also be viewed as self-adjoint. well, yeah, one has to define certain notions, but yeah, so that is another way of looking at these partial sums and the Fourier series. Okay. Now, you see, just the L2 theory is fine, because, you know, it also is not very, well, once you know everything, because of the orthogonality properties of these ENs, you know, it's fine. It's still possible because of this L2 thing. Now, you know, so mathematicians were not satisfied with just L2 average convergence. So, so in fact, you know, in 1927, Marcel Ries proved even more general result that for f Lebesgue measurable, so that this f is in LP of minus pi to pi, means that this integral minus pi to pi mod of fx p dx is finite. For p bigger than 1, this LP average also goes to 0. For p strictly bigger than 1, which also includes p equal to 2. Okay. So, and in fact, you know, this proof is a sort of convergence of other branches of mathematics. In fact, it uses functional analysis, complex analysis, and many of you might have seen this in a first course of Fourier analysis. So, so if this happens, if this equation happens, we say that Sn of f converges to f in LP, because it is LP average. Okay. And you see here p is strictly bigger than 1. So that time, of course, this was later, but in fact, before this was proved for p bigger than 1. So, you know, you may ask that why not p equal to 1? Because of this, the next thing which I'm going to say is because in 1926, Kolmogorov constructed an example of a function which is L1 integrable, that is integral mod fx dx over minus pi to pi is finite. Then this lim sup Sn of f mod f equal to infinity almost everywhere on this interval. So we cannot expect Sn of f converging to f in L1. So those who don't know, almost everywhere means that, you know, on a set, so this is equal to infinity, except on a set which is very, very small in terms of length. Okay. So you see, these partial sums are not successful in L1, right? So you might have seen this technique in your higher secondary, I don't know, or yeah, in your first year, that if, you know, if a sequence does not converge, then you try to take the mean of that and then try to see that if that converges. So this is Cesaro sum. So we define Cesaro sums and try to see that if at least this converges to f, because you know, this approximation of f by some nicer functions is always it comes very handy in lots of analysis, like in PDEs or you know, when you study inequalities. So this question actually is very important. And in fact, it happens if you consider the Cesaro sums of these partial sums, they converge to f in all LP for all p between, including 1 and infinity. And in fact, if f is continuous, sigma n, the Cesaro sum converges to f uniformly, in fact. And if it is, yeah, if it just continuous, so it sigma n of fx converges to f wherever it is continuous, and otherwise it just converges to the average of the left and the right limit of f at x. Okay, so these Cesaro sums are actually behave a lot better than the partial sums. Okay. So now this was all about the convergence in the average sense. So you see, now let us come to pointwise almost everywhere convergence. That is also something important for us. So now if we recall that the counterexample which was provided by Ramon only showed that given a continuous periodic function, its partial sum diverges at one point, which rules out the possibility of uniform convergence. So then, you know, given a continuous periodic function, it is then reasonable to ask, it was actually, this question was posed by Lucen, if the partial sums of f converge to f except on a small set. So here again, by small set means that they're small in the sense of length of that set. Okay. So, so before going to the result, we say that f is in LP, p between including 1 and infinity, if f is Lebesgue integrable, and this p integral mod f power p integral is finite over minus pi to pi. Then you see this question was posed in, I think, 1930s, I suppose. And then it took almost 30 years to prove something in the positive. So Carlson, he proved in 1966, in fact, that this is true, that if you have an L2 integrable function, then the partial sum of f converges to f almost everywhere. Okay. And subsequently, Richard Hunt in 67, he proved that it is in fact true for f in any LP, p between 1 and infinity. Okay, p equal to 1 is ruled out as because of the counterexample by Kolmogorov. So, and this remarkable theorem is also called Carlson-Hunt theorem. Okay. Okay. So, you know, the Fourier series are somewhat settled more or less because we have all sorts of possible results in the average sense, in the pointwise sense. Okay, so now let us move to generalizations of Fourier series. Okay. So we also have an analog of Fourier series for functions defined on Rn. So now the question here is that if we, so let's first define the Fourier transform of f. So yeah, there is a typo, it should have been minus. You see, if we recall that the Fourier series, how we define is you take f in a product with the exponential, where psi is just an integer, right? But on Rn, how do we do? If n equal to 1, instead of the integer, you vary psi over all r, and you take the f inner product, provided the integral exists, all of course, you take f inner product with this exponential e of I psi x, and you call that as the Fourier transform. Okay. And in Rn, instead of psi times x, psi is a vector, psi is in Rn, and x dot psi is just the inner product of x comma psi, where x is in Rn, psi is in Rn. Okay. So this is called the Fourier transform. And you see, so here Fourier transform is a function, and on minus pi to pi, it was just a sequence, right? Because it was just restricted on the integers. And in the partial sums, if you recall, let me just say that here. If you recall, there we were restricting these variable over a set, right? Which was mod n less than or equal to capital N. And here, what we are doing is we are restricting psi over a set over a disk of radius r. And then, of course, here we are integrating. It's like taking the superposition of this because psi is in the continuum. We cannot just do this discrete sum. There it was discrete sum, and here we are just integrating, right? And then the question is that as r tends to infinity, this sort of covers the whole space, right, in Rn. Does it converge to f or not? Okay. So this is the corresponding analogy here in Rn. Okay. And before going further, let me just say something here, that when n equal to 1, so the convergence issues can be handled as in the case of Fourier series. So basically, if you are dealing with convergence of these, they are also called partial sums. Okay, these partial sums on R, they are somewhat related to the Fourier series, which I'll not go into detail. And so, in fact, on R, the result is this, that if f is a Lebesgue measurable function such that this integral f of x mod p dx is finite, then these partial sums, they converge to f almost everywhere as r goes to infinity. Again, almost everywhere is, that's enough for us when you are just integrating functions. Its information except on a set of measure 0 is enough for us to integrate. So this sort of convergence is the best we can hope for. Okay. And so when n is strictly bigger than 1, it is not the same story. So before stating the results, let me just define something more. So we define SR alpha of f of x as this operator. Okay? This is integral mod psi less than or equal to r, and you have this function here, 1 minus mod psi square by r square power alpha f hat of psi e of I x dot psi d psi. Okay, and you see, when alpha equal to 0, this corresponds to the partial sum which we had just considered over here. But when alpha is strictly positive, this can be related to the Cesaro sums. For example, for alpha equal to 1, this is related to the Cesaro sums, and for alpha in between, like fractional Cesaro sums. So it's like, you know, when you make alpha strictly positive, it sort of improves your the sequence which you are making to converge to f, right? Because of this alpha positive, it becomes a better function. So the averages are more regular in that sense. So that is why you consider this sort of generalized partial sums. And in fact, they are also called SR alpha, are called Bochner-Ries means of index alpha. And they were first introduced by Bochner himself in his paper Summation of Multiple Fourier Series by Spherical Means, which was published in Transactions of American Math Society. So now, you know, of course, this question makes sense in n equal to 1 also, but n equal to 1, alpha equal to 0 is completely solved, and then alpha positive, it becomes even better. So let's ask this question, that for what alpha, SR alpha of f converges, sorry, it should have been converges to f in LP of Rn as R tends to infinity, when n is bigger than or equal to 2. Because when, so more precisely, so when does this happen? That is integral SR alpha of f minus f mod p dx, it goes to 0 as R tends to infinity, whenever this integral is finite. So when alpha equal to 0, you know, these are called the partial sums. And in 1971, so Charles Pfefferman proved a very surprising result, which implies that this SR alpha, SR0 of f, which was the thing which one starts with initially, it converges to f as R tends to infinity in LP if and only if p is equal to 2. And of course, n is bigger than or equal to 2, because n equal to 1, as I told you, that it is very similar to Fourier series, because it's just one dimension. But in higher dimensions, you cannot have this convergence in LP unless p is equal to 2. And that was something which was very surprising for all, for the mathematicians. And let us just try to see that why would, you know, why it happened. So one way of looking at it is this, that when n is equal to 1, you see here when we are considering these partial sums, so you see, as I told you, that the regularity of this, it depends on this function here. When alpha equal to 0, it becomes just a characteristic function of the disk of radius r, right? Because it is 0 outside the disk and it is 1 there, okay? And yeah, so when n equal to 1, this is the function in SR0. And when n equal to 1, what is this? It is just the characteristic function of the interval from minus r to r, right? Because mod psi less than or equal to r is just that set, the interval, where chi a of psi is equal to 1, where this is the notation here, when psi is a is in capital A and 0 otherwise. So basically this function is 1 on the disk, on the, sorry, n equal to 1, it's on the 1 on the interval, minus r to r, and 0 everywhere. So you see this function, if you draw the graph of this function, it will have a jump discontinuity at these points, psi equal to plus minus r. That is why we call it has a singularity, right? This is somewhat singular. But then there are just 2 points here. And on the other hand, when n is bigger than or equal to 2, if we consider this function, it has a singularity on the sphere, right? Because let's see what happens for n equal to 2. This function, this is a characteristic function of the disk of radius r, right? And then if, so basically the set where it is discontinuous, it will be the circle, right? And so the geometric structure of the circle is very different from that of the endpoints of an interval. And also in high dimensions, it will be sphere, and yeah, well, you can just call it sphere for all dimensions. So yeah, this is one of the reasons that, you know, things are not the same in one dimension as compared to higher dimensions. And also, you know, this proof, if you see the proof by Charles Pfefferman, it involves the existence of Kakeya sets in R2 having full Hausdorff dimension. Okay. So here, so the Kakeya sets, they are compact subsets of, well, which have a unit line segment in every direction. Okay. So of course, you can get many examples of such sets, but then, you know, there are somewhat, there are, so I think it was proved in, I think 71 only, that every Kakeya set will have full Hausdorff dimension in R2. And in fact, it was proposed by Besikovich in 1917. And yeah, so Kakeya sets actually can be very, very small also. I think Besikovich himself constructed an example of a Kakeya set which has 0 Lebesgue measure. Okay. So now you see, for n bigger than or equal to 2, alpha equal to 0 is sort of settled, right? Because of the result by this result by Charles Pfefferman, it converges to f if and only if p is equal to 2, right? So now we can ask that, you know, it is known. So what happens for alpha positive? No. Here alpha positive is, you know, when alpha is positive, you have this operator here. Okay. You have a better function other than alpha equal to 0. And so yeah, so for n bigger than or equal to 2, it is known that for a fixed alpha, the necessary condition on P for SR alpha F to converge to F in LP is this. That is, P has to be restricted in this range. So this one can prove without much difficulty. But then the sufficiency part is still very much an open problem. And yeah, it's n equal to 2 is settled, and n bigger than or equal to 3, it's still going on. And so, you know, still an open problem, but there has been a partial progress in solving this problem in the last 50 years. So recently, very recently, so Larry Guth and Ned Scadds, they developed a method called polynomial partitioning, which involves ideas from algebraic geometry. And they have been able to use this method very efficiently in proving lots of open problems. And it also helps to, improve the range of, you know, it helps to prove this conjecture for some range of P, you know. And yeah, so it's still and it's till now it still is, you know, it's very exciting for mathematicians to work in this problem. And now it has, so it started from Fourier series, and then it has developed into a completely different sort of territory, which involves algebraic geometry and lots of ideas. So that is something which is remarkable, I think. Yeah. So so let me just go through the references which I mentioned. So the first one is So this one was the book which Fourier wrote, which is called The Analytic Theory of Heat in 1822. And then here was where Dirichlet proved the convergence, the first sort of convergence of Fourier series. And this was where Raymond proved the counterexample. And here also in Kolmogorov proved a found a counterexample whose Fourier series diverges almost everywhere for an integrable function. And these two papers, they proved the almost everywhere convergence of the Fourier series by Hunt and Carlson. And so yeah, this is the remarkable paper by Charles Pfefferman, who proved where he proved the multiplier theorem for the ball, which was for which I just stated. And then these two this paper, Larry Guth, this was one of the earliest papers where they incorporated polynomial partitioning in proving results in analysis. And then that resulted in something improvement of the Bochnery's conjecture. And this is, I think, this is the latest paper, which again uses polynomial partitioning as a very important tool in proving the Bochnery's conjecture. And finally, the convergence of the Fourier series. Yeah. Yeah, thanks for your attention.
Thank you, Jyoti. It was really a nice talk. I enjoyed it thoroughly, and it was a good journey. Starting.
Yeah, it was just a journey.
Yeah.
It would have taken me more lectures to actually, explain. Yeah.
Yes, and it was good that you kind of like gave the journey because they are just new. I mean,
yeah, exactly. Just to motivate them to come into Fourier series, like an advertisement for that.
Let's see if there is any question.
There is a question. So as alpha is 0, then what are function properties? So let me go back to the, so alpha equal to 0, which function are you asking here? This one? So yeah, as I told you, when alpha equal to 0, this function, it has a singularity, right, on the boundary of the ball. Right? And so is there anything else written?
No, I don't see any.
No, there is something more written in the chat. Yes. Okay. Yeah. So is that what you're asking? Right. So that I already told. That yeah, when alpha equal to 0, this function. So you see, that's what I was saying. That if you make this function better, these. So basically, you are taking the superposition of nicer functions. So the resulting function, when you are integrating over these nicer functions, the resulting function which you get is it behaves better than what was for alpha equal to 0. Right. So if alpha is very, very large such that it is also differentiable, then by using some techniques you can prove that this function this will converge to f yeah, for I think with some decay also perhaps. Yeah. Is there any other question? Yes. So what is psi in slide 14? Let me see. 14. This one? Okay, this is a variable. This is in Rn. Is that what you're asking? Yeah, this is a variable. Like I told you, that in Rn, the Fourier transform becomes a function. Like on the circle, on the interval, it was a sequence. So here it is a function because psi is varying over Rn. So this is a function. And then you take the Fourier transform, you multiply it with a characteristic function of the ball of radius r, then you multiply it with this exponential, then integrate. The here the summing means integrating. No, in you cannot just sum like discretely here, so you integrate.
Hey Jyoti,
Yeah, hi.
Cesaro.
nice talk. A very good
Yeah,
overview.
thanks. Yeah, it's
Subject.
just a journey.
No, that's important.
Yeah, well, I missed a lot of important things also because then that would have been more technical also,
No,
I
I think
suppose.
for many students, I think a lot of students are there, it seems.
Yeah, exactly. For students only. This was meant for students. So yeah, if you if
Yeah.
yeah, if if you think not for you, sorry, for the students, that if I just sort of jumped over something.
Okay, that's a question.
Yeah, there is something. If f is in wk comma p log, can we say that partial sum sequence converge to f in wk comma p log? Here you are saying that well, yeah, okay. When p equal to 1, you need somewhat more regularity. When p is bigger than 1, yeah, one can prove that. Yeah, I think there are some results for that. Yes.
And there's one more question above. I'm not sure I follow that question though. Means function must be continuous and differentiable, right? Probably they had been asking somewhere what you had mentioned.
No, when alpha is 0, it is continuous and differentiable except on the boundary of the ball, right? Because the same person, yes, he asked me that
Yes.
as alpha is 0, then what are function properties? Yeah.
Okay.
So it's not continuous and differentiable everywhere. It is except on the sphere. Yeah.
Okay. So are there any more questions? Okay, if not, so let's thank the speaker. Thank you, Jyoti.
Yeah. Thank you.